And so I'm Sarah Harris from the University of Leeds, and my area is biomolecular simulation. So I am a very heavy user of HPC, including GPUs. So on that note, can we return to the fabulous question that we had and recast it a little bit and ask the panel, what can AI and simulation learn from each other in terms of how much processing power we are using and how we can make it more efficient? So would you like to, who would like to start?
Maybe Shantanu talked something in the simulation and AI, or I can.
Please go ahead.
I think using this one might be a good idea. We'll just pass it around.
Yeah, so I think we heard, starting from Shantanu, Adam, Mark, we heard a lot of things. I think especially what Shantanu presented, like this coupling, the surrogate models kind of things, if we can have AI-driven simulations to really cut down the overall execution time and the need for all those large-scale GPUs, but still achieve the same end results. I think that way, I think both the simulation is learning from AI, and then AI also is being benefited by simulation. So I just want to, I'm basically supporting your thoughts. You can add more to that.
Sure.
So I'm not the best person to talk about traditional HPC. We have a ton of colleagues that deal with that. I don't. But I know for a fact that I have a colleague in Switzerland she's working on ERF2. So this is our initiative to create like really large-scale system and software package for modeling climate for various applications. And some of her neural network based models for weather simulation, they run 50,000 times faster than traditional code. And after several days, they diverge in a similar way to traditional HPC. So I'll leave with that, and we can introduce appropriate HPC colleagues that are specialized in this to comment more. On neural networks front, right now there is unquestionably a bit of a hype around those models. Those models are admittedly extremely capable, and countless people are trying to make a living out of them one way or another. So I don't know exactly which article you've referred to, quoting the power consumption of those models, but I would be able to bet that if we were to take the author of this paper here and ask that person, how the hell does he know how much GPT-4 actually consumed in terms of computational time, since this is not public information? Yeah. Or if we were to ask that person, hey, have you ever heard about GPTQ or QLoRa, and do you know that it's now possible to do 3-bit quantization? By the way, those neural networks can operate with int3 precision, no problem, with 3 bits of information. And then that person would very likely not know that those things even remotely exist. So a lot of things that you'll find on Google, people, they just mocked on napkins without any consideration around what is the reality. There is huge amount of work by NVIDIA and by the entire community to very dramatically decrease the computational footprint of those models, both at training and inference. So Llama 2, for example, it's not just a vanilla transformer neural network with vanilla transformer layers and multi-layer perceptron, 2 layers at the end of every layer. It's now this thing called group attention. It uses fused flash attention 2 mechanism to manage the access to memory during execution, because those models are by far memory bound. You can make them network bound if you neglect what you're doing, and you can make them extremely network bound. Like I have a group of colleagues that are working on a subpar system that are seeing only 30% of the performance of our Selene cluster. But if you do things correctly, those models are memory bound, and there's tremendous amount of research around lower precision training. So those models are right now trained with FP8, full stop. And they are inferred with 3-bit integers. And I think that's not the end of the story. We'll make dramatically more progress around inference, because it's necessary. Those are large language models in the end.
probably don't have much more to say. I think there is general agreement in the scientific community that you can't continue to solve partial differential equations or differential equations generally the way we have if you want to study larger problems or bigger, better, faster, whichever, and sometimes all three. And you need to think of different ways, and this is why physics-informed neural networks.
Sure.
ForecastNet is just one example.
Oh yes, that's
right?
what she's working on.
But every domain is coming up with its own, if you will, large language model. Within the DOE, again, there's something called the Trillion Parameter Consortium, trying to think of a ChatGPT for science. But even as this project has been ongoing, we notice there are ChatGPT-4 like capabilities in every domain. Back to the real question, I think if you look at the scaling laws of how much data is needed as a function of the number of tokens and training, the problem lies there, as I think you pointed out and as others have pointed out. The amount of training is significantly greater than Moore's and Dennard. So where are we going to get the computational capacity? And there are developments, I think they're called tiny LLMs or baby LLMs, almost an oxymoron. But the point here is that they are more data efficient in a different way than just sample efficient, right? And so I think the point is where back to the coupling point, I can get the citation of the paper. It's not more of the same data, but definitely. Multimodal data.
Very aggressively cleaned.
Right.
Yes.
Multimodal data is better than more of unimodal data. And this is again why simulations, where you can generate different types of data through the simulations, are a great way to train LLMs.
Sure. No, definitely. By the way, all of that is not new. I strongly recommend you search for Rich Sutton's Bitter Lesson. It's a very good two-pager. Please read it.
That's wonderful, thank you. So do we have any other questions or comments from the audience? Yes, please.
Coming back to the last presentation, you quite nicely demonstrated if you make your data set larger,
Sure.
you are getting basically in a nutshell better results out.
That's correct.
Wonderful. So if we take the largest data set we currently have, which is called the internet, and chuck that on your neural network, forget about power, we've got unlimited power in my simulation. Does your code become self-aware?
And would that be responsible?
Sure.
Would it be responsible for it to become self-aware or not?
I would have no clue how to even start building something that is self-aware. Like this is not what we are building. We are building, the only thing that those neural networks can do is calculate the probability of the next word. So you put a sentence in and they say dog, 0.007%. Cat, 0.0001%. House, 0.001%. That's it. That's the only thing that those neural networks can do. They cannot do anything else. I personally, and I challenge anyone from the academic community we have no clue how to even start making them self-aware.
Okay, that's brilliant. Thank you. Would any of the other panel like to comment on that, or?
Not on the self-aware part of it, but there are aspects of responsible that we might get to.
Oh yes, whenever you design an engineered system, it needs to work.
Yeah, I think I'll not be adding anything. I think there are some more questions we can.
Okay, yes please.
2 points I want to bring up.
Sure.
One is model collapse from not getting enough fresh, new, unique data where it's just training over and over again and collapses. The other one is what happens if some of these copyright and intellectual property suits come through and data has to be withdrawn? Doesn't that mean an entire retrain from scratch of LLM?
Sure. So there are several dimensions to the answer. One, I cannot answer. Like I do not claim to understand international copyright law. Yes, we have a team that is specialized in that, and I'm extremely surprised if everyone else doesn't, that are looking at the problem one by one. So I do not know the answer to that question.
Model collapse is more of a rally.
Sure.
the
So,
first part.
by model collapse, you mean like it diverging and exploding during the training process?
No, it's if
Sure.
you don't get enough fresh, new data,
Sure.
that essentially the outliers get averaged out,
Yes.
which
So,
makes it dumber.
so in a sense, I think people right now those models are memorized very well. At pre-training stage, they are very sample efficient, and there are some studies showing that if you show the same sample to the neural network more than 4 times, it doesn't add any value.
Well, it actually can take value away.
Yeah, sure.
It gets dumber.
But I think this is, in a sense, maybe a wrong way of looking at it. Like a smart human being, no one is expect that person to know every conceivable thing. A smart human being is expected to know how to take an unknown problem, disassemble it into pieces, and step by step investigate. And I think this is what those models are doing already. Every customer I talk to is now super excited about this new term that people call it retrieval augmented generation, or open domain question answering, where we effectively allow the neural network to find its own information. And that seems like a much more sustainable way of doing it. I'm not sure whether we figured out how to do it perfectly yet, but I'm not sure whether trying to make sure that that neural network knows everything about everything is a sustainable way to do it. And
Yeah, it's not-
when it comes to removal of data from neural networks, there are some beautiful studies where people are investigating individual neurons, and they can make almost surgical-like interventions to the neural network, forcing it to believe that Paris is the capital of Madrid and so on and so forth, but we don't know how to do that. So like, the only robust way of removing data from the neural network would be not to show it to it. And even in that situation, I'm not sure how is that going to be possible, because the scale of the data sets are so vast that you cannot just look at it. Yes. So that problem will have to be addressed.
I'll give you like an example. I mean, I do a lot of work looking at how we human beings work. If you think of all these like whatever phase we are in the learning and all, we can just relate to our own training. Okay?
Yep.
So let's say whatever we learned over the years, it takes some education or experience or training to learn something, but then the world changes. My daughter thinks that I'm a dumb guy, okay? Because she got exposed to different kinds of data or different kinds of learning, okay? So I'm good if I'm a model, think of like a model, I'm valid for some time, okay? So then the other models or the new ideas are coming with newer data, they can supersede me.
Yep.
There is no doubt, and we should just admit that.
Yep.
So that's how I believe these models and all will keep on
Yep.
growing with newer data, newer environment, newer things. And since mankind has existed for so many years, thousands of years, I'm sure this AI will take it to the next level. There's a little bit of philosophical answer, but that's how things have
But
evolved.
admittedly, we don't know how to do online training of those models. We cannot just, memorize this little thing for me, please. No, it doesn't work like that.
So
That's a multi-stage process.
there are 2 other questions, and I'd like to take the one that is most focused on simulations. So are either of these questions anything to do with simulations? Okay, you're a bit iffy, so yes, please, go for it. If you can frame it in terms of the panel discussion, that would be wonderful.
I'll try to, because it covers aspects of the talk about the workflows and your answer just now. One of the key points that I try and drive into all of my junior people is reproducible science. If I'm continuously training my AI to do my simulation, how can then I reproduce that output? Every time I go through my process again, I'm going to get a different output. So how can I maintain provenance with an AI-based system that's going through self-training?
So how do you make sure that the piston in your car works for every one of the cars that you manufacture, or the air blades that
If I have a fixed model, if I have a fixed neural network, then it's fine. But if I start adding more data to it,
Sure.
then I'm going to start getting different results.
But my answer,
I don't put new
Sure.
bolts onto pistons.
you kind of do throughout their iterations. But my answer that I was alluding to was just test. Test, 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 and then more tests. So you have a new model, you have an existing suite of tests that are sufficiently covering the problem that you care about, that are providing you, I don't know, statistically significant evidence that it still has the same properties, and you re-execute that suite of tests. It's painful, it's time-consuming, but that's the way to do it, like in every other correctly engineered system.
So you have to go back. The problem here with the scientific method relies on the fact of documenting how you did something, giving it to someone else, and making sure they can reproduce it. If you can't do that, the whole basis of modern knowledge is destroyed. That's the scientific method. So here, you just roll back to that version of the net.
But you can't easily roll back.
Well, you can't roll back.
No,
the whole
but you
scientific
cannot.
process breaks down.
But that is, I think, not correct. So you built an instrument to test some hypothesis, and you describe the function of that instrument, but someone else that is reproducing that instrument doesn't have your instrument. They have a different instrument that is created out of different alloys of steel, has sourced a silicon from someone else, potentially completely. It's a different instrument. The only reason why you trust it is because you've tested it. But neural networks in the same way.
Shantanu, please.
So the question and the problem resonates entirely, and I don't think there's a complete solution, but there are emerging solutions, and there's a paper at eScience from 10 days ago. The reason why this is such a difficult problem is twofold. One is just the fact that you've got a lot of data that you're adding to a neural network and training, and it has different amounts, varying data, different amounts of data, different snapshots. It's a temporal dynamic problem, and you use that to steer simulations, for example. And so what was the state of the neural network? It's not an intellectually or a conceptually difficult problem. It's just a very difficult provenance graph management problem. It's challenging, but it's not something that is completely unthought of, unknown about. The reason why the second part, though, does get challenging is adaptive execution. Adaptive execution here means you are making decisions on what to compute or what to do next based upon the data. So in that sense, if you have any uncertainty, it propagates. But more importantly, like any chaotic system, if you don't have complete information, you lose the ability to retrace. And that is the problem when simulations are being driven by neural networks. It doesn't have to be LLMs, it could be any, which are being online trained. So no solutions, but we are working on it, and the paper that I alluded to at least tries to formalize the problem better and breaks it into these two, if you will, different distinct aspects, and says, okay, for the moment, let's try to capture as much information at the state at which the decision was made. And that's better than not, but obviously there's aspects that we don't have.
I'd love to see the paper.
Well, that's fabulous. I would really, really love to continue this discussion, but unfortunately I will be in trouble with our fabulous people who serve us lunch. And so can we thank the audience and the panel members very much?